If black holes are supposed to be perfect prisons, how can they ever change? For decades, the popular picture was simple. Cross the event horizon and everything is gone forever, including information. But there's a crack in that story that Stephen Hawking opened in 1974. He showed that black holes aren't completely black. They emit radiation as if they have a temperature. And once you take that seriously, you stumble into a deeper puzzle. How can a black hole's entropy increase without violating the laws of physics? Even stranger, the radiation doesn't just happen. It triggers a runaway accounting problem for entropy. Not runaway like a fireball, but like a logic loop, where every correction feeds the next, forcing the universe to keep revisiting what information loss really means. Before Hawking, the framework was the classical theory of gravity. Einstein's equations gave black holes with event horizons that seemed mathematically absolute. In the classical picture, mass could fall in, increasing the black hole's size, but nothing could escape. Meanwhile, thermodynamics tells us that systems have entropy, a measure of the number of microscopic ways to realize a macroscopic state. For ordinary objects, entropy always grows unless you're careful. The clash was obvious. If black holes only absorb, what happens to entropy and to information? Jacob Bekenstein took the first step by arguing that black holes should have entropy proportional to the area of their horizons. But without Hawking radiation, that claim had no physical mechanism. Hawking's work supplied the missing why, and it did it using quantum theory in curved spacetime, where the vacuum isn't empty, it's restless. Here's the core mechanism. Imagine the region just outside the event horizon. In quantum field theory, what we call vacuum is actually a sea of fluctuations, virtual particle-antiparticle pairs that constantly flicker into existence and annihilate. In flat space, they typically cancel symmetrically, but near a black hole, the geometry stretches spacetime in a way that ruins the balance. The event horizon acts like a one-way boundary. A fluctuation pair forms, sometimes one particle falls inward while the other escapes to infinity, because the escaping particle is not paired with its partner that remains accessible to the outside world. Observers far away detect a real outward flux. Hawking's calculations show that this flux has a thermal spectrum, with a temperature inversely proportional to the black hole's mass. Smaller black holes are hotter. Now for the entropy runaway. Hawking radiation carries energy away, so the black hole's mass decreases. As the mass decreases, the temperature rises, which increases the rate of radiation. That creates a feedback loop. Evaporation accelerates as the black hole shrinks, but entropy is where the runaway accounting appears. If the black hole has entropy proportional to horizon area, then as the horizon area shrinks, the black hole's entropy decreases. Meanwhile, the emitted radiation is hot and carries entropy into the outside world. The total entropy, black hole plus radiation, can still increase, but the precise bookkeeping becomes delicate as evaporation proceeds. During the early stages, the radiation looks almost thermal, but as the process continues, the radiation is no longer just energy. It's correlated with the black hole's internal degrees of freedom in a way that must preserve unitary quantum evolution, if unitarity is true. Those correlations are subtle, and they mean the entropy of the radiation doesn't behave like a simple steady growth. It should follow the page curve. Radiation entropy rises, reaches a maximum around the page time, and then begins to fall if information is not destroyed. So how does Hawking radiation trigger the runaway? It begins the chain reaction in which the black hole must both lose mass and expose information in the correlations of its outgoing quanta. Classical intuition says the horizon is a boundary that hides everything. Hawking's quantum result says the boundary is also a thermal machine. That forces an incompatibility to confront itself. Either information is truly lost, or the emitted radiation must encode it, which implies the entropy accounting has to correct as evaporation proceeds. The runaway is the demand for reconciliation. Each step of evaporation changes the thermodynamic parameters, which changes the entanglement structure, which changes the entropy flow, which in turn reshapes what missing information could possibly mean. Broader implications ripple far beyond black holes. This is one of the clearest laboratories where quantum mechanics and gravity disagree on basic expectations. Thermodynamics emerges, but from space-time geometry. Temperature appears without any conventional heat source. Entropy becomes a property of the horizon, suggesting that microscopic degrees of freedom are encoded in ways we do not yet fully understand. The black hole information problem is not just about what happens to astronauts. It's about whether the laws of physics treat information as fundamental or disposable. If Hawking's cephalohorrical calculations suggest a thermal, seemingly featureless emission, then the demand for unitary recovery is like asking the universe to rewrite its own ledger after it has already performed the payment. Modern approaches, holography, quantum extremal surfaces, and the idea that space-time geometry itself is emergent from entanglement, try to explain why the entropy of radiation can bend back down. Hawking radiation becomes the stress test that any theory of quantum gravity must pass. When you trace the story all the way through, the logic tightens. Hawking radiation arises because quantum fields near the horizon experience asymmetry. One member of a virtual pair can escape. That radiation carries energy and entropy outward, shrinking the black hole. The shrinking raises the temperature, accelerating evaporation and making the entropy accounting increasingly consequential. What began as a modest quantum correction to black hole nothingness becomes a runaway conceptual engine, forcing the universe to decide how entropy and information coexist in the presence of horizons. So the next time someone says black holes are simple cosmic sinks, remember the twist: Hawking radiation turns them into thermodynamic objects, and the entropy bookkeeping turns the process into a self-referential challenge, one that grows more urgent as the black hole disappears. If you want more on the ideas that reshape how we think about reality, subscribe for the next deep dive.